3x minus y equals 12, what is the value of 8 to the x over 2 to the y? So a lot of you look at this and you go, OMG, there's no way I can solve for x or for y over here, and then how the heck am I supposed to know what x is and y is so I can plug them in? So I can understand why this might stump a lot of you, but it's actually way easier than it looks. This is a little pattern that I like to call equation expression. I talk about this if you have my ACT math books. I talk about this in my ACT math books and the algebra books. And what I love about equation expression is there's always a single way, typically probably 90% of the time, that you can use to solve these. And once you know that technique, this seemingly hard question becomes pretty easy. And that is we substitute. So when you see this equation expression pattern, and again, that goes in this way. We have an equation here, and then we have an expression here. Don't worry about the fact that this has two variables in it. Don't worry about the fact that this has two variables in it. Just isolate something over here, and then plug it in over here. And you can even group substitute sometimes, and what I mean by that is you can isolate something big and ugly. Like if this had a 3x in it, you could isolate the 3x and then plug in for 3x. So you can group substitute, whatever you need to do, but you're gonna isolate something over here, and then you're gonna substitute. And what I always like to say is isolate to eliminate. So that's my basic strategy. The other strategy that I could employ here is I could also work backwards if I wanted to, and I could do that by looking at this expression here as an exponents expression. And I know whenever I have exponents and I want to simplify, a good rule of thumb is to get everything into the same base. So I can see right here, this 8 is like 2 to the something, so I could like get all that in the same base. But I'm gonna do the substitution thing first, and then we'll go from there. Okay, so I'm gonna subtract the 12 from this side, and then I'm gonna add the y to the other side. Okay, so I'm adding y and I'm subtracting 12. For those of you who are trying to track what I'm doing. So I'm gonna get 3x minus 12 equals y. And again, that's just basic algebra. I add the y, I subtract the 12. I'm kind of like switching sides and switching signs, right? So we get 3x minus 12 is y, and then all I have to do is plug that in right here. And so I get 8 to the x over 2 to the 3x minus 12, okay? And now here, this is cool because if I can just get these bases to match, then I can use this exponents rule, right? I can use like 2 to the a over 2 to the b equals 2 to the a minus b, right? This is an exponents rule. And if you don't remember this, then it's a really good idea to review your exponents. So here's how we do this. I'm gonna put this in terms of 2. So that's gonna be 2 to the 3rd quantity to the x, right, on the top. And that's gonna be over 2 to the 3x minus 12. And then you see here, this just simplifies to 2 to the 3x, right? 2 to the 3x, and then that's 2 to the 3x minus 12. And then all I have to do is this, right? A over b, I do a minus b. So I'm gonna do 3x minus that. And I get 2 to the 3x minus 3x minus 12. And I always insert that in parentheses. Don't forget the parentheses, really important. And then we distribute the negative. That becomes negative 3x. That becomes positive 12. And do you see how my 3x's cancel? Because if I have 3x minus 3x plus 12, boom, those cancel, and all I get is 2 to the 12. And that's answer choice A, and I'm done. Cool? So this might look hard. It really is not that hard. It's pretty easy. I isolate, I substitute. I then use the idea of make your bases look alike, and then I apply an exponent rule. Boom, done. Easy. I could do it probably really fast if I wanted to. But now you know how to do it really fast. And we're done. Okay, one more question I'm gonna go over with you guys, and that's 19. So this question, for all you smarty pants out there, you might be able to read this and then instantly know the answer. And that's how I am. When I read this, boom, I know the answer like super quick because I know a principle of math that basically tells me what the answer is. But if that's not you, well then I'm gonna explain how can you derive the answer and figure it out, and then what is that super cool hack shortcut that could have gotten you the answer in 10 seconds. I will get to that at the end of this explanation. In a right triangle, one angle measures x degrees, where sine of x is 4 over 5. What is cosine of 90 minus x? So a lot of people see this and they're like, OMG, not only do I have to run some sort of trigonometry because I don't know what x degrees is, but I'm in the no calculator section, people. So I can't just crutch on my calculator and make my calculator tell me what angle this should be by doing arc sine or something. Oh no, right? So how do we do this? This is crazy. Well, first thing to do whenever you have a right triangle is set up a SOHCAHTOA triangle. And it's like a good problem solving technique, okay? So that's what we're gonna do here. And I'm just gonna set this up. Remember, sine is opposite over hypotenuse, right? From SOH in SOHCAHTOA. Do you remember SOH in SOHCAHTOA? That means opposite over hypotenuse is equal to our sine. So if I make my little angle here, we'll call this angle x. And then I know my opposite O over my hypotenuse equals 4 over 5. Now, a method I can use to solve down triangles like this when I'm just working with the trigonometric functions is that I can use sort of like a reference triangle, and I can just pull the top off of this and set that equal to my opposite. I can pull the bottom off this, set that equal to my hypotenuse. So we go here and we see that. Now I can instantly fill in that this is my adjacent and it's going to be equal to 3. We don't actually need this, but you see how I can see this as a 3, 4, 5 triangle? I just fill in everything I know kind of as I go when I don't quite know what I'm doing, so that I can get my baseline, right? And I can see that right away. How do I know that? That's a Pythagorean triple. If you don't know the Pythagorean triples, they're really good to know. 3, 4, 5 is the most common one. All this is 3 side lengths that form a right triangle and work with the Pythagorean theorem, right? Because 3 squared is 9, 4 squared is 16, and 5 squared is 25. So this is just a squared plus b squared equals c squared. And if for some reason we actually needed to solve for the a, we could use the Pythagorean theorem. Again, we don't really need it. I'm just filling in everything I know as I go that's instantly coming to me. Let's talk about cosine of 90 minus x. Now this might seem tricky, but let's think about this. We have a right triangle, right? So if this is x, guess what 90 minus x is? That's its complementary angle. Guess where that is in a right triangle? It's the other angle over here, right? So this is 90 minus x, which brings me to a fun fact that you can memorize, which is that there is a relationship between complementary angles and their sine and their cosine, okay? So if I'm looking for the cosine of this angle, guess what that is? That's ka of SOHCAHTOA, or adjacent over hypotenuse, right? And what's the adjacent here? The adjacent here is actually what was the opposite of this other angle, right? Which is 4. And my hypotenuse is 5. So this is now equal to 4 over 5. If I'm looking at this angle, right? This pink angle. Cool, right? Which brings me, like I said, to this fun fact, which is that if you have 2 complementary angles, right? And complementary angles are any 2 angles whose sum to 90 degrees. The sine, if you have complementary angles A and B, the sine of A equals the cosine of B. And the sine of B equals the cosine of A. So the sine and the cosine are like reversed. The sine of this angle is going to be the cosine of this angle. And the cosine of this angle is going to be the sine of this angle. So whenever we have complementary angles, that's how it works. This is obviously a proof, so like you don't need to get stuck on a question like this. On the SAT, sometimes things are thrown at you that like, oh my goodness, like it's presented in a way where you don't instantly realize a relationship that if you think about it, you would go, oh yeah, I think I kind of remember that from trig class or from, you know, working with right triangles. It kind of rings the bell, the idea that the sine of this is going to be the cosine of this, or the cosine of this is going to be the sine of this. So if you knew that going in, when I read this question, for example, I went, oh, that's easy, 4/5. I literally just read it and I knew it. So if you have that memorized, this quote unquote hard question can become really easy, really fast. It doesn't have to be hard. And at the same time, it doesn't even have to be hard if you can't think of that right away, because you can always just draw out your right triangle, think about what you know, think about what this means, and just take it one step at a time. My best advice for you guys is a lot of questions on the SAT might seem hard, and a lot of times they are not nearly as hard as they look. So if you can just dive in the water, start swimming, start solving down, and have a little confidence that you can do this, you're gonna be able to solve more than you realize. Obviously, if you look at something and you have no idea how to do it and you want to skip it, and that's part of your strategy because you're not finishing on time otherwise, you know, do what works for you. If you need to skip problems, come back to them. But all in all,